We got one last example to chat about here with optimization. That last one was fun. What's next? This one will give us just a little bit something different. Find the point or points on y equals 4 minus x squared that is or are closest to the point at 0, 2. Okay, so we have this parabola, y equals 4 minus x squared. What is the closest point on that parabola to the point at 0, 2? You kind of imagine, how is this relevant? Right, so we're thinking like 0, 2 is not obviously not on the parabola, but it's sort of this parabola sort of passing around it. And we'd like to know like what's the shortest distance. Immediately what I think of is like, something in orbit. It's sort of passing by like a comet is passing by the Earth. And we want to know, well, what's the closest point that comet would come to the Earth? I'm sure there are lots more applications that are not on that sort of a scale. But that's immediately what I think about. Okay, let's get to it. Let's check it out. Here we go. Find the point or points on y equals 4 minus x squared that is or are closest to the point 0, 2. Okay. First thing we need, a drawing. Well, this one's maybe a little more straightforward. We're going to draw that parabola. We're going to plot that point. What would this parabola look like? You could certainly do this sort of a thing in Desmos or something like that. But maybe you remember, y equals 4 minus x squared. So that's a parabola pointed down. The vertex is at 4. So it's going to look a little something like this. Okay, and there's 4 at the top. The point 0, 2 is right there in the middle, 0, 2. Okay. So we're thinking, where's the closest point on that parabola? And, it's possible from my drawing that it could be up at the vertex. Maybe that's the closest. But I think it's going to be somewhere kind of like at a little bit of an angle like that, if I had to guess. So here's what we'll do. Let's label the point, kind of like in the last one, as XY. See if I can get a little bit more light, this can focus a little bit better. Okay, I think that's better. We're going to try and figure out where that point is, x comma y. What we're trying to optimize here, we're actually trying to minimize, is this distance between them. We'll call it d. And of course, this is y equals 4 minus x squared. Okay. So let's begin with that distance. Since this is what we're trying to minimize, can we describe that distance with an equation? Yes, you might remember the distance formula, the distance between 2 points. If you do, go right for it. It's based on the Pythagorean theorem. If you were to create a little triangle here, here's how it goes. The distance would equal the square root of, and you take the difference of the x coordinates, here x minus 0 squared, and you add the distance between the y coordinates squared. Again, that's based off if you were to make a little triangle there and use Pythagorean theorem and solve for d. We can simplify this just a little bit because of the minus 0. Square root x squared plus y minus 2 squared square root. I would suggest don't FOIL out the y minus 2 squared. Let's leave it like that. Okay. Looks good. So far, so good. We got our distance in terms of x and y. What is the constraint? Turns out the constraint, the other equation we need, it's the equation of the parabola. It's the y equals 4 minus x squared. Why would that be? Well, the constraint here is that the point xy lies on somewhere on the parabola. So we know it has to make that equation true. Whatever the values of x and y are, they've got to fit y equals 4 minus x squared. Kind of similar to the last example where we knew x and y had to lie on the circle. Okay. And also, what's also convenient, right? This is already solved for y. So we can take 4 minus x squared, plug it right in. D equals square root x squared plus 4 minus x squared minus 2 squared. And let's start to simplify this. X squared plus 4 minus 2 is 2 minus x squared squared. At this point, we might as well multiply all that out. I think it will actually be simpler that way. So let's see here. This would be plus 4. Inside outside would be minus 4x squared plus x to the 4th. Okay, and then finally combining x to the 4th minus 3x squared plus 4 with the square root. Excellent. Looks good. We got our distance just in terms of x simplified. Okay. Something a little bit different about this question at this point. Think about it like this. We're trying to minimize the distance, right? What x value will minimize d? That's the goal. Okay. Well, if we can figure out the x value that minimizes d, isn't that simply the x value that minimizes what's inside the square root? I mean, if we minimize what's inside the square root, we've minimized d, right? The x value that minimizes x to the 4th minus 3x squared plus 4 will minimize d. And hopefully you agree, yeah, if we just minimize what's inside here, you know, yeah, we still got to take a square root, but that's the x value that will do it. Okay, well, if that's the case, then why even bother thinking about the square root? Here's what we're going to do. We're going to create a new function. Let's call it f of x, just equal to what's inside there. If we minimize f of x, like if we find the x value that minimizes f of x, then that's the same x value that minimizes d. Now, why would we, ignore the root? Because we have to take a derivative, and I would much rather take a derivative of just this than do the chain rule. I could do the chain rule, but right, we got to set this equal to 0 and solve and stuff. this is gonna make things a little bit faster for us. And we're gonna realize the same X value that way. Okay. Simply minimize, simply find the X value. That minimizes this instead. Okay, excellent. We still need an interval or a domain of X. Let's think about this. For the domain of X, I'm going to go back to the drawing, back to the constraint. You know what I realized? There's another point here. This is symmetrical, isn't it? There will be a second point. Now, we only need to find the one point because then we'll know where that is. It's just got the negative of the X coordinate. But okay, there will be two. Maybe you realized that earlier as well. But we're only going to focus on, again, just on this half of the parabola. What are the extreme values for X? Well, X could be 0. It could very well be that this point at the top is the closest point. I don't think it is, but that might occur. What's the biggest that X could be? You're thinking, well, we're looking at this entire right side of the parabola. So X could be infinite, right? This parabola extends infinitely far, out. So obviously an infinite value of X is not going to minimize that distance, but there are points out there. So we're going to say from 0 to infinity, infinity with the parentheses. Okay. Very good. Never had an infinite as a possibility for an absolute max, but okay, we'll see how it plays out. We're good. We got our function, we got our domain. Let's find f prime for x cubed minus 6x. Where will that equal 0? We could factor out 2x, leaving 2x squared minus 3. And so 2x equals 0 will give us 1 critical. 2x squared minus 3 equals 0. Okay, so that's x squared equals 3 over 2. So x equals square root 3 over 2. We don't need to worry about the negative because that would be outside of our domain. So far, so good. Let's also check where the derivative is d and e. Well, for our f of x, we don't have any, none. For f prime, I should say. All right, cool. We got our two criticals. We realize this is on the edge of the interval, so kind of see that again, but okay, we got this other one as well. We need to plug both of these back into our f. Actually, we have a choice here. These, right, remember these values minimize f, they also minimize d. So we could take those values and actually plug them into d and figure out which one will create the minimum distance. Let's do that. D equals square root x to the 4th minus 3x squared plus 4. Plugging them into d of 0, what would that be? Well, 0, 0, 4 square root is 2. Okay, yep. We knew this already, right? If we made x 0, then the distance from the point up to there would be 2. Makes sense. How about for that square root? D of square root 3 over 2. This is interesting. Well, turns out because of our even squares, our even powers of x, makes it a little bit easier. So we'd end up with, let me write it out. Plugging in there, we'd square and then square again. So squaring would get rid of the square root. Squaring again would give us 9/4. Then putting it in here, squaring is 3 over 2. Then times 3 is minus 9 over 2 plus 4. What's that going to leave us with? 9 over 4 minus 9 over 2 plus 4. I got the square root of 7/4, which we could just think is the square root of 7 over 2. What is that? Maybe as a decimal so we can compare. This is about 1.32. So that's definitely less than the point at the top. Okay, so far so good. We tested the 0. How about the infinity? Yeah. Technically, you can't plug infinity in, but what we could do is take the limit as x approaches infinity for D. Plugging in infinity, well, infinity, right? The x to the 4th would take over and we get infinite. The square root of infinity is infinity. So we'd end up with an infinite distance. Makes sense, right? If the x coordinate of our point is infinity, it's infinitely far away from our point at 0, 2. So the idea is to minimize. We got it right there. There's our absolute min. All right, our work is done. We just have to make sure that we answer the question like we're supposed to. What did they actually ask? Find the points. Okay, so they didn't want the actual distance. What points on our parabola? So we go back, we realize, hey, this occurred at x equals root 3 over 2. So we know the x coordinate of one of the points. What is the y coordinate there? You say, all right, looking back. No, I think I need to go back to this page. We can find the y by plugging our x into the parabola. Y equals 4 minus x squared. Doing that, 4 minus 3 over 2 is 8 over 2 minus 3 over 2 is 5 over 2. So there it is, the closest points. There are 2 of them. One of them is at root 3 over 2, comma 5 over 2. And the other one has the negative x coordinate of this one, same y coordinate, negative root 3 over 2, comma 5 over 2, the other closest point. And we did it. Hey, let's really quick, I'd like to graph this over in Desmos. See if I can pull that up. Go. Y equals 4 minus x squared. Okay. And let's put the point at 0, 2. Okay, so we came up with square root, there it is, 3 over 2, comma 5 over 2. And the other point was at negative square root 3 over 2, comma 5 over 2. Yeah, that looks pretty good. I mean, it's hard to eyeball, right? But The point at the top is 2 away. This is definitely closer than that. Yeah, there we go. Closest points on the parabola. So you can imagine like if there's a comet kind of sweeping around the sun or sweeping around Earth, how close might it come to us? Again, I'm sure there's other maybe slightly more applicable things to us than that, but yeah, pretty sweet. We found it. Look, I mean, isn't that incredible? Like the closest point, and it took a couple of pages of work, but we're able to perfectly, precisely identify it. That is pretty amazing. Okay, you guys, that is it for optimization. A challenging section for sure. But hopefully now you're prepared for the homework. You are prepared for the homework.